Welcome to Frost Astrophotography. In this video I'm going to take a closer look at SH2-157 or the Lobster Claw Nebula. The Lobster Claw Nebula, or SH2-157 in the Sharpless catalog, is an emission nebula in a constellation of Cassiopeia, and it is located about 11,050 light years from Earth. The majority of the yellow-orange part of the nebula has been shaped by the stellar wind from several giant stars, and it is comprised of mainly hydrogen alpha. The bluish areas of the nebula consist of mainly highly ionized oxygen and other gases. As you will see later on, in the middle of the hydrogen alpha area there is a small intense planetary nebula, and on the outskirts of the nebula you will find an open star cluster, also called NGC 7510. I'm just finishing this season now in terms of image processing and making videos, although the date for the last night with astronomical darkness here at 63 degrees north has already passed, and that was April 11th. Data for this image was gathered over the course of 3 nights at the 7th, 14th and 18th of March. The total number of light frames for this image is 163, and the total integration time is 13.6 hours. So let's jump into PixInsight to look at some processing steps and the final image. The season in total has been a real catastrophe in terms of how many hours I've been able to use my equipment and gather data for nice images, but you will see that later on when I finish my review of the 23-24 season in that video. I was able to gather some data at the end of this season, and the Lobster Claw Nebula here is one example of that. When I had the opportunity to gather 163 5-minute light frames over the course of 3 nights in March, and this was actually the first time, I think, that I was able to use all of the calibrated light frames. I did not have to discard a single one. Now, if that is due to the selection process of me, or if the data was actually good, I am not going to investigate further, but I didn't see any big problems with my data. So I've gathered 74 light frames of HA. I've also gathered 44 frames of S2 and 45 frames of O3. Interesting phenomenons here is the open star cluster down to the right here. And this is NGC 7510, or the Arrowhead open cluster. There are a lot of other names also, the jewelry box I've seen, but it does resemble a triangle here, as you can see. In the final image that you will be presented with at the end of this video, you might not see it so clearly as here, because I will have reduced the stars a bit, because the main feature of this video is the Lobster Claw Nebula and not this open star cluster. There's also a small planetary nebula here in the center of the image. That is also interesting, but far too small for me to do anything with my focal length, I would say. But it's nice to know it is there. This processing was fairly straightforward. I started off with the 3 master and stacked light frames of H-alpha, sulfur 2 and oxygen 3, and those were also drizzled 2 times. I didn't have to do much cropping since I gathered the data for this image during the course of 3 nights in March 2024, so there's no rotational difference or anything like that. The conditions were similar and the data was very good, but I did a small crop of the image anyway. And when that was completed, I used the new process here of gradient correction, and I used the default parameters in this tool to correct any gradients that were visible in the image, but fairly small differences, I would say. When that had completed, I used the dynamic background extraction to differentiate a little bit between the nebulosity here and the background, as I normally do. It was fairly easy here because the nebulosity is fairly concentrated and not scattered around the whole frame. A linear fit was then performed with the H-alpha as a reference, and then I ran the blur exterminator and the noise exterminator. So we can compare the first image here to the last in the linear step. As you can see, we have a very good results on the nebulosity and the stars in the image here. If we, for example, zoom in on the double cluster here a little bit, you can actually see the difference here in the image without noise and blur exterminator in comparison to the image to the left here with noise and blur exterminator. I would say get PixInsight and get those 2 processes instead of buying a very, very expensive telescope. Well, at least as a first step. I did, of course, run through the processing steps on all of my light frames for all filters, but if you have watched my videos in the past, you will know that I usually don't show the processing of all separate filters, since the steps and results are very similar. The first part of the non-linear phase is to make starless versions of all three light frames and filters. And in this case, when I was finished with that, I noticed that I had a lot of noise in the background. If you're comparing the image to the left here, that is the Sulfur 2 starless version, with the image to the right, that is also the Sulfur 2 starless version, but with some of the background removed. This was done using a ranged mask and curves transformation tool to slightly adjust the brightness and contrast between background and nebulosity. Now, you really have to be careful with this so you don't accidentally remove some actual data that you want to have in the image. I might have done some of that, but it's hard to differentiate sometime what is nebulosity and what is light pollution or other things that you don't want. Looking at the O3, you can also see that you have a lot of light pollution here. This whole part to the left here, I would say, is light pollution. Other than this small portion, maybe. And I carefully used the same mask here just to make sure that I can remove some of the light pollution in here. For H alpha, I usually don't need to make any adjustments whatsoever. Just a very, very slight adjustments to make it a bit more distinct. Now the next step in the nonlinear phase is to combine the three starless images with the modifications done to the background or not, if you choose to do it that way. And I normally use pixel math for this. And be sure to uncheck use a single RGBK expression here, and then you just insert the name of the light frames SH and O, and you select S for the red. So just to make it a bit more work, I called mine S2 starless BG for background, and this is HA, and this is O3. And then you just execute this using the square. I always forget. And then you are left with an SHO, combination of your three different filter light frames. The next part doesn't really differ much from my usual processing. I take my SHO starless master image here, and then I run SCNR on it to simply remove some green and magenta in the image. Some people want to keep it in there, some people do not. Other people want to maybe remove some of the green, but not all of the green. I really don't like magenta type colors on stars or nebulosity, so I really want to remove that. I usually remove 80% of the green in the image as it is, and then invert the image and remove 100% of the green to get rid of this magenta here. The next step is to adjust the colors a first time. I usually do that a lot of times during the nonlinear phase, and there are several ways. There is no way better than the other. Maybe it's a personal preference. You can make color masks that you apply, protecting other areas than the color you want to change or alter, and simply use the curves transformation tool to adjust the colors of your choosing. I usually use a script in the toolbox here, selective color correction. I think this is a really good script, and you can create automated masks here for different colors, for example. If you simply want to manipulate red in the image here, and you can also adjust luminance, saturation, and contrast for the entire image or for portions of the image using the different mask options up here. As you can see, in comparison between the two, I've adjusted the luminance, I've adjusted the brightness and contrasts of certain areas, I've enhanced the red areas here, making them a little bit more orange, so to speak. Next step is to sharpen the nebulosity, and I usually use multiscale linear transformation tool and unsharp mask to sharpen areas. Let's see if we can zoom in on an area here. And if you compare the two areas here, I hope I'm at the correct zoom level. Yes, you can see that this area is not as sharp as the area to the left here, even though the changes are a bit subtle. If you zoom out, you will see that you have achieved some sharpness in the image here, and that is what we are after. Subtle but noticeable zoomed out changes to sharpness. You also want to make some noise correction in the image here. I usually use TGV denoise, and there is a slight difference between the two here. You can see that there are a little bit more noise in the image to the right compared to the image to the left. Now you can run through this 1 or 2 or 3 times, just depending on how much noise you want to remove without losing other things in the image that you want to preserve. After that, it is time to do some more color adjustments. You may want to brighten some areas even more, or simply adjust other colors some more. And as a final step, I sometimes select to use the script dark structure enhancement, which really make some of the dark structures in the image pop out. As you can see here, in comparison to the two, I like it sometimes. I don't like the result other times, so I might try it out and use it or not use it. First image to the right here is the first original integration, and on the left you have the processed SHO ready to be integrated with some stars. Lately I've been using SHO stars. Initially in this hobby I used a lot of HA stars. I would say if you are able to and have the opportunity and time, it's great to have RGB stars, I would say. But SHO stars also works nice, in my opinion, after you have processed them a little bit. When you simply join SHO star versions, you will get something like this, and it's not a pretty sight. You will have to do the same procedure as you do with the starless versions, and that is run SCNR to remove magenta and green from the image here. I then also try to make some subtle color adjustments to maybe enhance or have a better contrast on some of the blue stars or red stars. Then of course I don't really like to have this amount of stars in my image. You can see that there are a lot. This is the open star cluster down here. But I don't want this amount of stars, so I usually reduce the stars quite a bit. This is the difference between the original stars, in size anyway, and the reduced stars on the left that I will use for this image. You can see that they have been significantly reduced. Comparing the first image here, that is SHO integration without any processing, and the image to the left here, which is a processed image of the stars that also been reduced. What we have now is the final starless and the final stars image. We are using pixel math again with an integration, this time a single RGBK expression, using this formula, which actually integrate the images inverted. Execute this and you end up with an image looking something like this. And as you can see here, we have experienced some of the things that we don't want. After we join this together, you see that we have some magenta in the star there. Therefore, I usually do some final color adjustments. In my case, it includes another SCNR run and some color adjustments along with some brightness contrast, adjustments, because the integration process adds a little bit of brightness into the image. So you can see here on the right, we don't have that magenta glowing star that we don't like. That has been removed, but the size of the stars here, I would say, is good. So here is the final result of my Lobster Claw Nebula SH2-157, and it is 163 light frames with a total integration time of 13.6 hours, gathered during 3 nights in March of 2024. Data was of course gathered with my miniature home observatory, and if you haven't watched that build series, I would highly recommend that you check out my videos on building my own home miniature observatory. And that is of course located in the backyard of my house here at 63 degrees north with a portal for sky. Please enjoy this image, and I will see you in the next video. Thank you so much for watching this video, and if you like it, please give it a thumbs up and consider subscribing to my channel if you're not already doing so. If you want to support me and the work with these videos, there is an option listed in the video description that you can use. Until the next video, I wish you have clear skies.